How's everyone tonight? End of the week, for some of us anyway. I have no classes on Friday, but conferences and stuff. Okay, good news. Tonight is kind of a slow down or easier concepts. Most of it will be graphical, so we look at a graph, we know the high points from what's the highest point, the low point from what's the lowest point. We're tying in two sections. But the hardest part of the second session is not really the topic or the calculus, but setting up the problem. So we'll talk about those. I think I sent out an announcement, but I moved all at least this is what should have happened, all the due dates for everything from 11/3 forward to just after spring break. I think I made it the Tuesday after spring break. With the goal of trying to get you through it all by then, if at all possible. I can move for another week if we need to, so let me know, but it would be probably in your best interest to have at least the homework done by this time. And then, I'm not sure what I did with these. I think that's what I did, and then I think I just moved this one to here. I might have moved these two as well, but some of them the latest due date is basically the night of the exam. And again, everything should be done by then, but you should also have the time, give yourself the time to go through the reviews and such. So, but pace yourself, do what you need to do to learn the topics. But so far, as we got through 11.6, these are all the different ways of taking derivatives. Today, we're going to look at some more simpler ways because what we're going to do is now we're starting to do some applications. Everything actually will be an application of the derivatives, taking a second derivative of a derivative. Related rates will get back to 11.6, so if you had a little difficulties with them, don't scramble too much, just maybe wait till here and it might make more sense when we put it in a context. So we'll be good, and that'll get us really good shape by spring break. Elasticity uses some of these, and it's a business concept, and I believe most of you, or some of you at least, will have had some experience with that concept of elastic demand and elastic supply, and all we're going to do is look at sort of a formula that we use calculus to be able to calculate those things. And then we'll have some review in our exam. Okay. Any questions as we move forward? Good. Okay. So then let's go back into Canvas. We're focused on the new materials for test number 2. We're going to look here at 12.1 and 12.2. So there is should be a recording for each section we've gone through. There's also down here prior lectures from the prior content, although this section is, they're using pretty much very similar problems, so that should be, these older videos should also be helpful, maybe more helpful, because, I don't know, so take a look through those. Also, as you go through, I opened up this last night, I think, or Tuesday night, or whenever I did, Wednesday. So this is the review. Now, this is all based on the last time I taught it. However, I found there was a lot of similar stuff in the reviews, so there's a study guide here with no answers. There's video solutions to the first part, the second part. I don't see 11.3. I think 11.3 was actually on the other one, but you'll see it integrated in here. And since they had 11.3, we'll see what they give us as far as newer stuff as we get further along. So as soon as I do have the new practice test, I'll get that posted. We'll get you some videos for those as well, but this is a pretty good way to go through, especially if you're struggling with any of these sections. You might come in here, take a look at what kind of questions were on the study guide, and then I give a direct solution video where all I'm doing is showing how to solve it. And if you might find similar type questions, and that might be an easier way to get through things. But take a look at these. What's this one? Also, this was an older one. They don't do this anymore. They used to have the test reviews actually in WebAssign. So you can at least see what the question is, and I'm taking derivatives, so there's like 10 questions here, 10 questions, so there's a lot of ones. Fast forward through till you find a question that maybe you're struggling with, the sample type, see how it was solved, and again, that might be helpful. So just resources from older stuff of going through things. So those are there. And again, we'll get as I get the new stuff, we'll have it there, but we've got those. Okay. I did cut off quite a bit of actually this slide deck that the textbook company gave us. They went into, you aren't missing anything, but the homework we have is very visual. It's looking at graphs. When it's not, they give you a function, and what I'm going to ask you to do, or suggest that you do, is graph it with the graphing calculator. I'm going to use Desmos and I would suggest actually using Desmos to start, even though we can't let you use them on the exams yet. But then, because it'll help you understand the concept real easily, and then learn how to use your graphing calculator to solve them, for test problems. Okay. So we're just looking at some applications in chapter 12. So maxima and minimum, or extrema. So extreme values. Maximum, well, let's just get into it. What is a maximum? Well, there are two kinds of maximums. One is a relative maximum, which would mean it's sort of like the top of the mountain or the top of the hill. It might not be the very top, but it's the top of its local area. Okay, so all the places the birds like to hang out at the top, right? So locally, so we call that a relative maximum or a local maximum, but relative because it's in its area, it's the tallest point. So I think of it as the top of the mountain, because actually on a graph, it's going to look like the top of the mountain. There's also an absolute maximum, which means absolute means the top of the universe. So that for at least that function, that's the very highest point of all time. So it could be infinity if it shoots off to infinity, or it could be just the highest point that's in the graph. So that it could have a limit, or it could go to infinity. Okay, but there's nothing higher than it. Nothing. Because if that was higher, then that would be the absolute maximum. So we can have actually multiple relative maximums, right? Because we have a mountain here, a mountain here. One could be higher than the other, but they're both relative maximums because in their area, they're the highest. One could be a hill, one could be a mountain, but we would consider both of them to be relative maximums. We can sort of technically only really have one maximum, absolute maximum value. We could have it occurring at 2 points because we could have two mountains that are the top of the function that have the same height. So there could be two places where that absolute maximum occurs, but they would have to be the same. There cannot be two maximum values. Because if one is here and one, because one would have to, a number has to either be bigger or smaller if it's different, right? So we'll take a look at that. So two kinds of maximums, and so how many kind of minimums do you think there's going to be? You guessed it, 2. And they're exactly the same. So we can get a relative minimum, and I like to think of that, it looks like the bottom of a valley, right? So on the graph, we're going to see we're down at the bottom. So that would be a relative minimum. And be careful, because sometimes when I talk, I start mixing these up when I'm talking about, but it's the smallest value, so it's kind of down and then it dips up. So that's in a neighborhood or in a small area, it's the smallest for that area. There's also the possibility, and usually there always is one, there's an absolute minimum, which is the smallest value, and again, that would be the bottom of the universe. So it might be negative infinity if the function goes all the way down, or it could have a bottom, but there's no other points that would be lower than that. Okay. And again, just like with maximum, we could have two different locations for an absolute minimum, but they would have to be the same. It bottoms out at negative 50, let's say. Could occur at 2 or 3 or 4 places, but there's nothing any smaller than that. Also, when we talk about relative extremes or absolute extremes, either maximums or minimums, we're talking about a point. But when we talk about the point, so oftentimes what they're talking about, they'll ask where is it located, and when they want its location, they're asking for its x value. So where's that maximum or minimum or relative maximum, where are they located? That's going to be referring to its x value. When we want to know what is the value of a minimum or a maximum, I got those backwards, but when we want to know the value, that's its y or its function value. Okay, so sometimes it's easy to kind of confuse them because it occurs at a point, right? It will have both an x coordinate and a y coordinate. The x coordinate gives us the location of that value. The value is from the y value. Using. Does that kind of make sense? And we'll see how they ask the questions, but whenever they're asking for what's the value of the maximum, you got to give them the y coordinate. When they ask where is it, you got to give them the x coordinate. Okay, and sometimes it's not as clear. So they're going to give us this example several times, and when we look at this, what do you see? Oops, I didn't want to go that fast. You see two mountains or hills, if whatever you want to call it, but there's a top, right? There's a top here and a top here. We see one valley, which has a bottom here, about here, so we're just kind of eyeballing this, and this is what we get to do. And then there's this place right here, which we might not think of, maybe we think of it more of as a crevice, but this is actually a place where we're going to see has a special name because we can't actually take the derivative of a point like that. We need a smooth curve. So this is a place where we have a sharp point. We can't take its derivative, but there is a relative minimum that occurs there. And we'll go through that a little bit. What about those endpoints? Could those also be considered? Yeah, exactly. So this would be a relative minimum because it's for its area, it's the lowest. Now it's not an absolute. These guys seem that they're smaller, but it's lower for what it's at. And this would be a relative maximum. And in fact, it might be, I think it is, the absolute maximum. We'll see. So we'll talk through this. But so here's where we look for maximums. If we limit the interval what we're talking about, if there's a beginning and an end, endpoints are very important. And they're also the places I forget when I'm on a test. I'll look everywhere else. I'll look for these mountains. I'll look for the valleys. I forget to think about the endpoints. But the endpoints are very often where a minimum or a maximum is occurring. Okay, if it has an endpoint. We're going to do some problems where they don't have endpoints. It goes on to infinity and such. But when they give us an endpoint, we've got to consider them. Okay, so we're kind of looking at where could there be some minimums and maximums. Again, but it's also at the beginning, I think the first 3 or 4 questions in the homework, they give you a graph. You just you locate it on the graph just like we did here. But they'll give you enough, they'll give you numbers that you'll actually be able to pick off what those are. We'll take a quick look at a few of those. So again, they're just taking us through, and they label them. They give them these names for where their location is. So these would be A, P, Q, R, S, B. Those are all x coordinates, right? And then if we wanted to get what the values are, what we'd have to do is we'd have to take that particular one and we'd have to come over here and read its y value to actually get the value, which we will be doing when we have a graph that has some numbers on that side. Okay. But we see and it identifies that P, R, and B are all relative maximums, right? Because they are maximums for the area they're in. One of them potentially could be an absolute, but even an absolute value, if you just call it a relative, you're right, it is relatively the maximum for its area. It also is an absolute. Okay, and we'll see they'll define B to be an absolute maximum as well a little bit later. But For now, they're just calling it relative. And then 3, relative minimums. I guess I should change colors, right? So A is a relative minimum, Q is a relative minimum, and S is a relative minimum. And again, because it's limiting there, one of those is going to be an absolute minimum as well as being a relative minimum. And they get a little wordy. I left this in just in case because you have access to them. But when we talk about a relative extrema, and they talk about it's coming from Latin, minimums, maximums. So we're looking for, when we look for the location of the point, that's when we're looking for the x value, and then we're comparing its y value. For maximums, we're looking for the highest points, and then for minimums, we're looking for the lowest points. Okay, so again, you can kind of walk through here, and again, whenever we're thinking maximums, it's kind of looking at things that would look like a mountain, a hill, or something like that. They give a little bit of mathematical definition, which we don't really need to use, but basically, it's a relative maximum if the point R, as they've got laid out here, if we could go to the left a little bit and to the right a little bit, and all of those points either to the left or right are smaller, their y values are smaller, that's what we call a maximum, right? It's just the biggest. And when we got the graphical look, it looks like the top of the mountain. Looks like the summit. That's all it's saying here. But they're using some math definitions of, go a little bit to the left, so h units to the left, go h units to the right, and those are all smaller than what the y values are all smaller, so hey, that's a mathematical definition of a maximum. Okay, so just to let you see it, again, we can get by without using that, but basically they're just getting very mathy here. When all the points are greater, right? The value at R, or whatever value we determined at the top, if it's greater than every other point that it's close to, that's a maximum, right? That's all this thing is saying. At least it's a relative maximum. Over here, if that point ends up that it's smaller than all the stuff, well, that's a relative minimum. Okay, and again, this R minus H, R plus H, kind of thinking of limits. If we go either way, everything else is either smaller or larger than it, then we've got a minimum or a maximum. But again, we look at the graph, we kind of know from intuition, we know what a mountain looks like, right? So we just kind of keep moving with that. And again, they get into this, that each time we're talking about a maximum or a minimum, it occurs at a point, so we have an x and a y value, and again the x will give us where it's located, the y gives us the actual value of the maximum or the minimum. And so they're going to talk about P and R, and obviously P is more maximum than R, it's higher, but if we look over here, what's going to give us the tallest? The absolute maximum is going to occur at B. Okay, and this would be the function value at B, right, the y value. But we'll see, we get a absolute maximum there. R and P are simply relative maximums. So now we talk about the absolute, and it's just got the definition that if we're on some interval, and again, these have closed brackets, so that means the closed interval, A and B are both included, that in this case, at the endpoint, we actually get the maximum, absolute maximum, right, the highest point. And again, oftentimes you'll find that that's what happens, is the absolutes oftentimes occur at the endpoints. Not always, but oftentimes they are. And oftentimes we forget about them because we're so especially once we get into this method, we'll see the way we find the internal ones is we take a derivative and we find where the derivative is 0, because what kind of a tangent line is there at point P? Tangent line is going to be horizontal, right? Horizontal tangent line has what kind of slope? Any kind of horizontal line has what kind of slope? 0. Good. So basically our method is whenever we want an internal maximum, we find the derivative, set it equal to 0, and that will give us it gives us a maximum, but it also would give us the minimums. So then we have to determine it, but it gives us the locations of what x value, what x values give us a value of 0 for the derivative. That tells us we've got a horizontal tangent line, and then we do the work. We have to find the values, the function values. We will have a few like this, and again, this one the derivative isn't going to exist here. It's going to be undefined, so we'd have to look at that graphically anyway. Okay, but the thing is we get into this process of taking the derivative, finding where it's equal to 0. But in that process, notice we found 3 places. We check those places, but oftentimes we forget to come back and check the endpoints, but kind of they should be in that list as well. We call all of these, I don't know that this book calls them because they give them some other names, but we call those critical values, critical points. If we have the x and y, these are places, critical values basically that we want to consider where a maximum or minimum could occur. Okay. And again, more definitions. The maximum means that the point is larger than every other y value on the function. A minimum, absolute minimum, means that that y value at that particular point is smaller than every other y value. Does that make sense? We okay to kind of keep going? Okay. So 2 absolute maximums. Wait, it has an absolute maximum at B, so they identified that there's only figure 2, not that there's 2 of them. So there's only one absolute maximum. We just absolute max, identify it that way. And then an absolute minimum, though, is right here, because this is a little bit lower than all the others. So again, this would give us our absolute minimum. And if we had numbers on this graph, we could actually look them up. We could find out what those y values are, what the x values are, and we could list those. And that's what we'll be doing in the homework. Okay, so for this section, for 12.1, we're either given a graph or we're given a function. If we're given a function, the first thing we're going to do is graph it so we have its graph. And we just look and say, there's the bottom of a valley. I mean, visually we see it right here. Right? We see it going down, coming back up. We see, if I do a tangent line, that's going to be a horizontal tangent line. But we certainly see, just by inspection, that's a low point. There's a relative minimum. Oh, and it's also the lowest point of the whole function, so I can also call it an absolute minimum. And we could identify it as a point 0, 1, which is where it's at, right? The value is 1. So the value of the minimum is 1. The location is x equals 0. Okay, so we have those 2 points. So the point gives us, the x value gives us where it's located, the y value gives us what the value of the minimum is. Is there an absolute maximum? What does that tell us? I guess there is. What would the absolute maximum be? Infinity. Right, there you go. Sometimes it depends on how the question is. They say, well, that's unbounded, so they don't call that a maximum, but it is. You can't really ever get to infinity, but that's what we would say. Okay, and again, we go through this, that the value of the minimum is the y coordinate, right? Y coordinate, and the location where it's at is always going to be the x coordinate. It's just kind of in the college algebra. If you took college algebra here, it's kind of critical because they have questions where they ask these and they're not very specific, but when you have to determine, are they asking for the minimum value or the minimum location? And this one's not as tricky. Okay, so here we got an example. We've got a graph, and it's probably some function. It's probably an x to the fourth type function. But what do we see here at a and b? Are those minimums or maximums? Maximums, because they're the top of a mountain, so they're the highest points around. They're relative maximums, and they are also absolute maximums, right? Because there's nothing taller, but we could call them relative maximums. While there are two of them, does that mean there are two absolute maximum values? No, there's the same value, whatever this is. We'll call it 10 because I want to give a number to it. So they both equal 10, so the value is the same. There's only one absolute maximum value, which is 10. There are two locations that occurs at. So that would be point A, 10, and point B, 10. So there's 2 points that are absolute maximums, but there's only one absolute maximum value. That's the important concept, is if you have an absolute maximum, there's only going to be one of them, one value. Could be 2 places it occurs, but only one value. Okay. So this is going to give us a way to locate them, and it's going to give us some names. So when we have an internal point, and we can see sort of either a mountain or a valley, we can see that there would be that we could take its derivative, and it would give us a horizontal tangent line. We call those stationary points. And again, that's important to use because the homework, they ask for these types of things. Okay, not all textbooks use this terminology, but stationary points. If we have a place where the derivative does not exist, we call that a singular point. And again, the only way that's going to occur is if we have a sharp point. So these are kind of but there's a few functions that do this, and usually it's involving a fractional exponent, like to the 2/3. We'll see. We'll take a look at one. But when you graph it, you get a sharp point, so you can't take its derivative. But we would identify that as a singular point. Okay, and then again, don't forget, they also could have occurred at endpoints. And what do we call the endpoints? Endpoints. So that's fitting. That's the easiest one to. I get the stationary and the singular because they both start with S. I don't know why they do this in math. They always name things that are closely related with the same first letter, like in statistics, mean, median, mode. You know, how hard is that to remember? All these singular and stationary. I get those mixed up, but we'll get through it. Okay. So one way we're going to see if we don't have the graph, or we don't have the means to make a graph, we can find the derivative and set the derivative equal to 0. That will give us all the stationary points, all the places where it's either a local maximum or a local minimum, because that's where the tangent line would be 0. And that's when we find the derivative, set it equals 0, we're finding horizontal tangent lines, right? So that's one thing we're going to be able to do. How do we find out if the endpoints are minimum or maximum? We find their location, plug them into the function to get the y values. So in the end, it's all about finding where those x values are, plugging them not into the derivative function, but to the original function, getting the y values, and then just putting them in order from smallest to largest. And then also having to look at them to see, we could get the y value, say on this one, but we need to know that that's going to be a minimum, right? A relative minimum. Whereas if we're at P, that value is going to be smaller than B, but that doesn't mean it's a minimum. It's because of the way it looks. We could take a look and see it's a maximum. Okay. Okay, and then this just talks some more. I left these in here so you could, if you're interested, you can read it later. But the stationary points, let me go back. Stationary points. Okay, stationary points are where the derivative equals 0. Okay, those are the ones we usually find. On occasions, we'll find those singular points, but those are pretty special functions that we don't use a lot, really. Okay, actually, absolute value functions have a V shape, so they will have one of those singular points, right? Singular values. Okay. Right. So a singular point is where we cannot take the derivative. And again, we go into it a lot, but I think there's only going to be one or two of these, and they're fairly specialized functions. Okay. And here's the word that we call all of these things we've been getting, what we call critical points, anywhere the derivative equals 0, because those are potential maximums or minimums. Okay. So a lot of it's just the terminology. And then again, always remember the endpoints could also be a place, and typically they're a place where they're at least a relative minimum or a relative maximum. They may be also the absolute minimum or maximum. Okay. So this is all the things we're looking for. So we're going to look at a graph, and basically where our intuition tells us there's a maximum, that's going to be the places we're looking for. Where it tells us there's a minimum, smaller values, that's where we're looking. And again, we always check the endpoints. So we kind of go left to right, check the endpoints. Or actually, I go from the two ends, check the two endpoints first, and then come inside and see internally how many places are there potentially maximums or minimums. Okay. And more things. So stationary points, again, that's where we can use the derivative if we want, set it equal to 0. We can also use algebra, and we can just use, I'm going to just use Desmos. I'm going to graph them, I'm going to click on it, and it's going to give me the values. I'm not even going to use calculus for the first set. The second set is where we might need to use calculus. But a lot of this we can do these with graphing technologies. Before we had all these graphing technologies, we had to use calculus. I mean, because we couldn't graph all these things. Or if we did, it was by hand. Okay. Singular points wherever the derivative is not defined. And again, it's usually that's a place where we end up with division by 0 or something like that, or we end up with a negative inside of a radical. But again, on a graph, that's going to look like a sharp point. And then also the endpoints we're going to check, and the way we check them is we plug those endpoints, we plug the x values into the function, and we get the y values. Okay. So whenever we're talking about extrema, we're always comparing y values. So we got to plug it in, get that y value, plug the x value into the function, get the y value, and then we can tell which y value is the biggest. That's going to be our absolute maximum. Which value is the smallest? That would be our absolute minimum. And checking on all the relative ones in between. Okay. So before we go into this, I'm going to backtrack a little bit. Let's go into the homework. See what time is it? Oh, we got plenty of time. Right. 12.1. Just going to view. There's, I think, yeah, eight questions. And what you're going to see is they're going to give you a graph, and then you're going to have to identify, and you can kind of see they've got them right here. So at -4, what do we have? What's that? We have 8, which is what kind of a, and it's that's the biggest of the bigs, right? So good, it's an absolute maximum. What they're going to want you to do is go from, let's see, how do they say this? Order your answers from smallest to largest x value. So they kind of just want you to go from the left to the right. So we really kind of want to start at this, what's this endpoint? What would we classify it as? Is that a minimum or a maximum, or is it just a point?
Relative minimum.
Good. It's because it is the lowest of all its neighbors. Okay, so we come in here, we say it's a relative minimum, and then we give its, and notice this already has a parentheses, so we're just going to enter in -12, comma, and what's the y value? 0. Okay. We'll go to this, what we identified. The next one, we got an absolute maximum. Now, we could call it a relative maximum, but since we only get to choose one thing, we want to give it its most specific name, so we'd want to say that's an absolute maximum. Okay. Relative maximum is also correct, but absolute maximum's more correct. Okay, so they'll, and again, we put the x value, which is -4, and the y value, which is 8. So that's the point it occurs at. -4 is the location, 8 is the value, and you'd go through and do that. And you see you see a minimum here, relative minimum, and also it's absolute minimum down here, right? This is going to be an endpoint, but it's going to be a relative maximum, again, because it's up there. It's higher than all of its neighbors. Okay, so you would identify those. Another one, just a different graph, endpoints, kind of do the thing. They let you know, oh, there's only 3, so it's kind of, just kind of giving you some practice going through. Here's one. What's happening here in the middle? Well, they're only telling us we've got one potential option. Are these endpoints? No, because there's no points, so this must keep going. So so on this graph, we're just going to identify this point here. So it's kind of helpful because they're kind of telling us how many there are. Okay. Then we get into some where they don't give us the graph, but they give us a function. So what should we do? Graph it. And I'll take one of the, let's see, I did this one. Here's this kind of a funky one, 2/3 power. Because I want you to see they're also giving us limits. They're giving us boundaries. So it's not going on forever. It's going from 0 to 2, and those are included. So I wanted to remind you, did I ever show you how to do piecewise functions in Desmos? Probably not. So I'm going to show you. Anyway, this is what's really cool about Desmos, is we can go in there, and that's what I think it's a great tool. So you go desmos.com and click on graphing calculator, or just desmos.com calculator. We can put that function in, which, what was it? It was something to the 2/3. Yeah.
I have 2, and then in parentheses, x minus 1 to the 2/3.
I think we're going to get the same thing. Let me just, okay. Oh yeah, I can go back here. X, yeah. So there's no red. We're all going to you'll have this exact same problem, but x minus 1. So we put in the function. We could just do y equals, what was it? X minus 1 to the 2/3. So I'm going to raise it to the 2/3 power. But notice it goes on forever, and the question is saying only go from 0 to 2. The way we can do that is if we put these little curly braces, and then we put an interval. So we're going to go from start at 0 is less than or equal to, less than or equal to. And if you want, with Desmos, you can come here and you can just choose them off of here if you'd like. So what are we limiting? We're limiting x, and then I'll use this again. X is also less than or equal to 2. And then I can put the other curly brace. And notice it's only going to give me the part that they're talking about. It makes it easier to focus on these endpoints. Okay, so let's kind of zoom in a little bit. So we want to find, so this endpoint's kind of nice because it gives it to us 0, 1. We've got an endpoint over here, 2, 1. Those are both what kind of extrema? They're absolutes, and they are maximums because they're high, right? This point down here, you can't take its derivative, right? Because it's one of these ones, but we can graphically click on it, and we see it is a minimum, relative minimum, but also a absolute minimum, and its y value is 0, so the value is 0. Its location is at x equals 1. Okay, so but that's how I encourage you to do. You can do all of these. All the other ones you can graph, and then just do it graphically, pulling off your points here. Okay, so then when I go back to my review here, got this, and they show us they got 3, and we did 3, and we want to go from left to right. So we remember we had an absolute maximum, and that was at 0, 1, and then we had an absolute minimum at 1, 0. So this is, actually I messed it up the first time I went through this. I transposed the numbers real easily. And then we had another absolute maximum. So see, we got two places, but the maximum value is the same at both. And that was at 2, 1. Okay, and you could check it. And the rest of these, graph them, and then they're telling you there's going to be 3 places where you get either maximum or minimums. Look at the graph and figured it out. Just looking at it, I couldn't tell. You could take a derivative, but you've also got to see there's one endpoint at 0, so we could check that. But there's no second endpoint. It goes to infinity. So these are always good ones to go ahead and graph them, and you'll see what's going on from there. Okay. Another one, you can graph it. Just graph it, and use that little trick with Desmos. If you forget, because I forgot, I just look up piecewise functions with Desmos, and that's where this concept comes in, because you need it with piecewise functions, and it's just kind of cool. You can cut off the ends. If you don't even want to deal with that, you could still get by and just manually do it. But the other thing you can do with Desmos that's kind of cool, you can actually do vertical lines. Like you could do x equals 0, which gives you that one, and then you could also do x equals 2. So you could do that for the endpoints if you wanted to. If you forget how to cut and you don't want to cut it off, you could do something like that. So that's the other thing that Desmos allows you to do once you've got a point. Do the vertical lines, and then once you've got those, Desmos is really good at finding intersections. So if you want a y value, you put y equals, and that gives you a horizontal line, and you can find that intersection. If you're looking for when x is this value, you can do vertical lines with Desmos. So, but you can't do that with a TI-84 calculator. You can do horizontal lines, but you can't do vertical lines. So it's kind of cool. Okay, so far we doing good? So before we get into back to the PowerPoint, what I'm going to show you is what 12.2 looks like. And they sometimes give us a function, like in this one, and then we're looking for maximum and minimums costs. And so we could do this, but this one we could do graphically if we wanted to. We could graph this. We'll see that it's an x squared, so thinking how does an x squared look, right? It's a U shape up or down, and this one has a positive, so it's going up. So it's going to have a minimum, so there'll be a minimum cost here. So you can go through with that. But some of them, the difficult part is they're word problems and you need to set up the equations. Okay, so some of the questions deal with rectangles. And they give you stuff like around what's the perimeter of a rectangle? How do you find the perimeter of a rectangle? They want to create a rectangular vegetable path fencing for the, so they're giving us fencing, which is going to go around the perimeter, right? So what's our formula for perimeter? Plus 2 width, yeah. Thinking back to geometry, which was probably 7th grade and haven't done it in years, but this is the hard part, because it's going back to stuff that, oh, you should know what a rectangle does. You know, you draw the picture, and then they give us that fencing for the east and west sides costs $4 per foot, so I guess that's the east and that's the west. So whatever this width is, so we're going to get 2 widths, right? And the cost of that is going to be $4 per feet. So I'll multiply that by 4. The fencing for the north and south sides costs $2 per foot. So that's a length at the top and a length at the bottom. So plus 2 L's. And that's a little bit cheaper. I have a budget of $80 for the project. What is the dimensions of the vegetable patch with the largest area I can enclose? So whatever this is, right, needs to be equal to $80, because that comes from the perimeter. But what is it that I want to maximize? I want to get the most area I can get, right? How do I get area of a rectangle? Length times width. So what you're going to do, I'm not going to solve this all the way, but you would, distribute this 4, this 2. What you're going to do is you're going to solve this equation up here for either L or W. I'll get it a little bit so you can kind of see 80. This will be 8W plus 4L. And then you want to solve it for either L or W. It doesn't matter which one, but you've got to get it solved for one of the variables. So then we can substitute whatever that is for either this L or this W. So then we have an equation that has only one variable. Okay. Maybe I'll go a little bit further. Would it be helpful if I went further with this? Definitely. Okay. So want to solve for W or for L? Someone choose one. Okay, let's go for W. So we're going to solve for W. We would subtract 4L from both sides. I didn't give myself a lot of room, so I'm going to go back up here. So this is now going to be 80 minus 4L, right? Because I subtracted 4L from both sides, so the 4L is gone, equals 8W. Is that clear? Is that what you see what I did? I just moved that 4L over to the other side, so it becomes negative. And then how do I get the W by itself? Divide by 8. So this is what W equals. So when I come down to my area function, I'm going to replace this W. So there's the L, the length. I'm going to replace it with this function, or this thing. 4L all over 8. That's going to be the area. I'm going to want to maximize that. What I'm going to do is multiply through by L, and you'll see I'll get that the area, and you'll notice you'll get something different than 80 because that's the red. The area is going to be, I'm going to just distribute this L through. I'll get 80L minus 4L squared all over 8, which you could reduce that if you want. But notice I've got a quadratic, and I've got the quadratic part, the L squared, has a negative in front, so what kind of a parabola is that? It's going to go like, I can get the maximum. Okay, when I get that maximum, it's going to give me an x value, right? A y value as well. But the y value is the area that I would maximize, but they don't want the area, they want the length of the sides. It's going to give me L, right? Because that's, I would graph this maybe with x's, L becomes x. So the location, the L part, the x part of this, that's going to give me the length, which would be the north and south sides. And then what do I do with that? I take that length, plug it back in up here, and I'll have my W. Okay. So a little bit of, you see, this is just it's a problem solving part of it. It's really not the in fact, we didn't use any calculus because we got the equation set up, then we graph it, and we find that point using graphical means. We could also take its derivative and set it equal to 0. That would help us solve. Could be, but I think that's a little messy. But graphically, we can get all of these. And it doesn't matter on a test how you do it, either way. But again, this whole section, and that's what we're doing too. The first section should be fairly straightforward and easier, just identifying minimums and maximums, 12.1. But 12.2, you're going to deal with these. I'm going to delete this off. So triangles, and again, this is another one, but these are kind of nice because they do give you a picture. You want to put a fence here, fence there, same type of deal. They give you some hints of what the area of a triangle would be, base times height divided by 2, so sometimes they give you a little bit of help. But again, it's setting it up and kind of walking through this. They give you some costs, they give you some maximum that you're going to be able to spend, and then you want to be able to maximize the area. Okay, so these are sort of a standard. We want to fence something in, so that gives us, we're dealing with perimeter, so there's constraints on that, but then we've got what we call an objective function area that we want to maximize. We want to get as much area as we can for a certain amount of dollars. Okay, and again, you could see the left border is $8. The lower bottom, so which one's you think going to be the bigger one? Well, the $2, you're going to use as much fence as you can, but you've got to use some on the other side. So it's kind of one of those things. And again, when they get done, they want what the border is, but they also want you to get us the area. So just kind of look at what they're asking us to solve for. Okay. Sometimes they do give us a function. What price will bring the greatest revenue? So if I guess let me talk here a little bit. So this function, they're giving us quantity, Q for quantity, how many we can sell. So this function tells us how many we sell at a given price, right? So if I know how many I could sell, let's just say 10, how would I get my revenue? You take the amount you sell times what? The price. So if I'm selling sweaters, sell them for $10, I sell 10 of them, I'll make $100. So this is so what you see is this is the quantity function, so quantity times price, that's going to be your revenue. And it's weird because you just take this 300,000 minus 15,000, and again you'll have different numbers. There's a P already in this, but it's kind of saying at a given price, that's how many we'll sell. You take all of that times the price, and that's going to give you your revenue. Okay. And again, we want to maximize revenue, and notice we end up with a quadratic. Most of these, that's what you're going to end up with, is some kind of quadratic. If you're not getting a quadratic, I would review what you're doing. That's mostly what you end up with. And quadratics have either a maximum or a minimum, depending upon what the leading. And in this case, since we're going to have a negative on the quadratic part, it's going to give us a maximum. Okay, and we can do it by taking the derivative, set the derivative equal to 0, and you might give that a try, but remember we could also do it graphically. And if you do it both ways, I think you'll get a deeper you'll see it, because the graphical way you'll actually see it when you take the derivative. Oh, it's got the same x value, right? Because that's what it's going to give us. When I set this equal to 0, I get that same x value as the maximum. And that'll help you with this one down here, where they give you quantity and price, and but they want you to make the greatest profit. So what is profit? So we do what we did up here to get our revenue, right? Revenue is going to be Q times price. So we take that function times price. Cost is how much? And this was on the test, except it was revenue. So if it costs us $4 to make, what would be the cost function? Each one costs $4. So simply the number we make, which is X. Oh wait. How many are we going to, so it costs $4 to make each copy. How many copies are we going to make? Well, again, that's determined by price. So actually in this case, it would actually be Q, 4Q. Okay, so you take that whole function times 4, that's going to be your cost. How do we get profit? You take your revenue function and minus the cost function. Okay, now this is going to get messy because 4 times Q is going to be, it's going to have 2 terms, right? Because our Q is actually a function here. We're going to have 4 times this, that's going to be your cost. You're going to have P times that, that's going to be your revenue. We're going to subtract the 2. And remember, when you subtract things with 2 terms, what happens to the negative? Because this is going to have a negative outside, right? Multiplied by 4. We have to make sure we distribute it through. Okay, so just, but it's all algebra. Okay, it's all algebra. Once you've got your profit function, we can figure out the P that will give us the best, because we'll get the greatest profit. As you can kind of see, this is going to be a squared, so we'll get a quadratic that's negative, so they'll have a maximum. Again, you could do it by graphing it, or you could do it by taking the derivative. And if we take the derivative of profit, what else are we getting? Thinking back a few sections. What did we call that when we took the derivative of profit? It started with an M, the marginal profit. Okay, but it will also tell us. So we could use that. It will tell us what price we should charge, so that we can maximize the profit. So, all right. Cube, length times width times height. So, and here they give you a function, so it's pretty well set up. Determine the revenue. This is and they give you your revenue. So you want to find the maximum. Again, you could just graph it. You'll be able to graphically find it. You could also take its derivative, set it equal to 0, solve for it. So there's a little bit more algebra in that. But that'll get you through it. And I'll go back to the PowerPoint, but the PowerPoint is really not very helpful in my estimation, because, where is it? We'll keep it. All it basically says is how to problem solve. So we'll kind of go through. It just says this is what we're trying to optimize something, either minimize cost or maximize profit. It says we have some constraints and we're looking for the objective function, so we were setting those up. We want to maximize the area, that's the objective function, right? Constraints come from how much are we willing to spend. So we only have so much fencing we will be able to buy. So those are constraints, and then that allows us to maximize it. And they give an example. We don't, as I went through, I want to go through the homework. We don't do anything with average cost, but if we have, so if this is the cost, what would be the average cost? Well, this is the cost of producing X number of items, however many X is. So if we divide it by how many we produced, right, that's the average function. It looks like we used to do that a lot. In this particular part of the course, they seem to have taken out most of the average cost. In fact, they took it out. It was earlier, they took it completely out. But if you ever want to talk about average cost, it's just what is the cost of all of them divided by however many we made. That is the average. So this is just the thing is, as you go through this process, you have to identify what are the things that are unknown, just like we did with that rectangle, length and width we didn't know. What is the objective function? What are we trying to maximize? Again, that one, it was area. So some of them we identified they want to maximize, and it's right in there. Maximize the profit, maximize the revenue, minimize the cost. They'll tell us what the objective function is. And they give the example, and this little bar just means the average cost, and so it's the cost function divided by X. We had to go through, identify the constraints on the problems we were working, right? We only have so much money to spend on the fencing or something. They gave us some constraint. We only have so much land we could do. And then, and again, this is in here, but we're not going to do anything with average cost here. This is mostly here. Step 4 is then to solve, once you've got everything set up, solve for the problem that maximizes it. So, if we want to maximize area, solve to get our area set up. Maximizing, either take the derivative, or my state, I think, first off, at least graph it. You'll be able to see, and again, fitting the window and everything, see where the maximum is, see where the minimum, whatever it's asking. You'll be able to find it real easy, And then maybe later on go back and try the algebraic approach or taking its derivative. Okay, and then there's a 5th step. So this is specific to this, so we're just kind of checking, do our answers make sense? And then they go to the graph. Okay, my suggestion is go to the graph first. You can clearly see the solution right here, right? There's a minimum. Boom, I'm done. And then go back and maybe play with I could take the derivative. When I set the derivative equals 0, I got 100. Okay. And then I would have had to plug that in and see that was the cost of $50. Okay, that minimizes the cost. Average cost is $50. So if I make 100, my average cost is going to be 50. If I make more, for some reason, the average cost actually goes up. Maybe I have to hire more people, or labor costs, those kind of things are actually going up. But if I want to keep my average cost down, I should just make 100 and stop. Better than, So, but the graph is very powerful, and I think by doing that, you'll get the concepts down a lot faster, catching any errors, and then maybe go back and we'll look at some later, So this is identify the problems, read through it, what's going on, and typically you'll have two types of equations. You'll have one with constraints. This is, the perimeter. This is what we can do. This is, or to give us some sort of thing. Then they want to maximize something else. They might give us the cost and revenue, and then it's okay, maximize the profit. Okay, I got to combine these things. So, and then once I've got my objective function, make sure I've got my constraints, because they might limit me. There might be some limits, so those are endpoints, right? I can only make so many, so that might be giving me some kind of an endpoint. Use the optimization problem, solve it, and then because some maybe endpoints, maybe you get a negative value that doesn't make any sense for how much fence I can make, so I throw that away. This one is too much. I can only make 500 things, and I got an answer of 1,000. Well, that doesn't. That's not in my interval. So throw those out. You get the final one. and you'll have your answer. But again, the homework actually helps you because they'll tell you how many maximums or how many values there are that you're looking for. And usually in each of these cases, there's only going to be one. We're looking for at least for that interval for what we're given, we want the absolute either maximum or minimum, not both. It's usually, and you'll see most of these, or actually I went through, I think all of them are going to end up being quadratic. So you get either a minimum or a maximum, but they give you that practice. And quadratics are pretty cool because they're pretty easy to take the derivative of, right? Because if you take the derivative, you get a linear equation. Linears are pretty easy to solve. So they give you that practice. But again, I highly recommend graphing it first because you can see the whole layout of the problem. Then come back and say, okay, if I take its derivative, hey, I'm matching the answers. Get a little bit of practice with both. Okay. And it won't let me go any further because that's the last slide. So that's really all 12.2 is. Take your time on it. This is stuff we can, like I said, we've got next week. We've got a spring break. I've moved all the deadlines to after spring break, so you fit it in where it's working for you. But certainly that 12.1 I would go through. That'll get you your concepts down on minimums, maximums, relative, absolute, those kind of things. This one is just a. Well, some of you may be very good at it. It's always the ones I struggled with, but set them up, do them, and we're good. Have a good weekend.